Hi everyone, I'm Brendan. I work for Polygon, and today I'm here with Bobbin for a Whiteboard series episode on STARKs. So Bobbin, do you want to introduce yourself?
Yeah, so I also work for Polygon, and basically I got into zero knowledge proofs and STARKs quite a while ago, like late 2018, and I've been kind of exploring and understanding them ever since and building a lot of tools around them, so happy to share my knowledge.
Okay, we're coming at you live from a basement in Amsterdam, so I'm really excited about this.
An art museum basement.
Yeah. So maybe if we start really basic, what does STARK stand for?
So STARKs is a zero knowledge proving system, and the acronym stands for Scalable Transparent Arguments of Knowledge. And you might have heard about SNARKs and STARKs, and so there's another big category, SNARKs. And a little known fact that S in STARKs and S in SNARKs actually stands for two different things. So in STARKs it's scalable, and here is succinct. And there is actually quite a big difference between the two. And another difference is that...
Wait, hold up. What's the difference?
So the difference, and I guess we'll get into this a bit later in more detail, but the difference is that, for example, for STARKs, you don't necessarily need pre-processing, and the program description is succinct.
So what does so S in SNARK stands for succinct?
Succinct, yes.
Okay.
So basically, essence means that the verifier is succinct. You don't need to. What this basically, it's exponentially faster to verify a proof than it is to run the computation.
So we have a big computation,
yes.
Small proof.
Yes, exactly. Small proof or fast to verify, and STARKs don't necessarily imply that what's scalable. Well, so scalable also means the small proof exponentially smaller than the computation. But they also imply that there is no need to do this extra step of pre-processing or taking the original description of the program and kind of like pre-processing it for the purposes of verifier to be able to verify it very quickly.
So pre-processing is we have this circuit or we have this program, and we basically take this long description and we compress it down to something that's much smaller that lets us verify proofs that use that same program.
Correct. And and then the other term is transparent, meaning that you don't need a trusted setup for STARKs, while you may need a trusted setup for STARKs.
So sorry to interrupt.
Yes.
A trusted setup is just when we want to build a zero knowledge proof, we have to do this thing that basically requires at least one person in a ceremony to generate a secret and throw it away. And if they don't, then people can forge proofs.
Correct. So ideally, we would like to avoid that. So these kind of, I would say, high-level differences, and they were much more important originally. Now the lines are blurring, so you can have transparent SNARKs as well, and you can adapt some of the techniques from SNARKs into STARKs. So there is much less distinction now. it's difficult to exactly say what is STARK and what is SNARK. But in general, like STARKs are transparent, no trusted setup. So if it's not, if it requires trusted setup, it's not a STARK. And then scalable as well. If you need pre-processing, you can also probably say that this is not a STARK. But the other thing is that N here stands for non-interactive, and STARKs don't have that N. So STARKs could be interactive, and in fact, sometimes there is benefits to be having an interactive protocol, like potentially smaller proof sizes. But you can also have a non-interactive STARK. You basically take an interactive protocol and use a Fiat Shamir to transform it into a non-interactive one. So
STARKs can be interactive or non-interactive.
Yep. So if I had to do it, I would draw like a diagram saying, this could be, STARKs, and this could be SNARKs. And if we put, the non-interactive STARKs would go here, and then scalable, transparent SNARKs would go here. So they're kind of an intersection of the two.
Cool.
And in general, when we think about like zero knowledge proof systems, I think there are two components that are used to build both STARKs and SNARKs. And the first component is called arithmetization. And the second component is polynomial commitment scheme. So you can mix and match different types of this, and I'll go into more details in a second. But you can mix and match different arithmetization and polynomial commitment schemes to get kind of different properties out of zero knowledge proofs. So as an example,
yes. Veil of ignorance here. What do you mean by arithmetization?
So arithmetization is a process of basically taking a program, right? So let's say we have our program.
So, and that's something in C or
C, JavaScript,
just,
whatever,
yeah.
like high-level language that people are used to. And we want to transform it into a statements about polynomials. We need to do this so that the proving system can understand. So basically you take a program and you do something to it and it gets transformed into a bunch of statements about polynomials. And this is something that a STARK or a SNARK system can interpret and generate proofs for. And then we need this polycommit scheme to make sure that those polynomials have bounded degrees of some sort.
Okay, so I take my program.
Yeah.
I turn it into some set of polynomials, and then the SNARK or the STARK verifies that some relation about those polynomials holds. And if that relation holds, then I know that my program or my statement is correct.
Exactly, the program was executed correctly. So basically the step of arithmetization is taking this program and applying some transformation to it to do this. And there are different ways to do it as well. So this one. So basically there are a very well-known method of doing arithmetization is called R1CS. Yeah. So R1CS is very frequently used in SNARKs, and
what does R1CS stand for?
It's rank 1 constraint satisfiability. If you system.
Yeah.
Maybe system. Yes. So and the other approach is AIR. And this stands for algebraic intermediate representation, or some people say arithmetical intermediate representation. There are different ways of thinking of how you take a program and describe it using polynomials. So in case of R1CS, you can think about a program as an algebraic circuit. And it is very similar to like an electronic circuit where you have a bunch of gates that are connected by wires, and you put inputs on those on the input wires and like some signals on the input wires, and those signals propagate through the gates.
But just to jump in, to be clear, that this isn't this isn't a circuit board that we're wiring up. It's more like a conceptual framework that we're using to represent.
So those are not physical gates, those what we call algebraic gates, or those gates can actually encode different things. So if we wanted to kind of, let me erase this. So if we wanted to like describe or draw out like a circuit, so let's say we have some inputs, we have some gates.
What do those inputs look like?
So these inputs could be, because the gate's algebraic, like in a traditional circuit, those would be like a signal encoding 1 or 0. But here it could be basically a value or a kind of an element in the finite field, usually in the context of kind of zero knowledge proofs. This could be an element in the finite field, which you can think of as a number. So we put some kind of a number here. It would propagate through the gates, and you can connect them in various different ways. For example, let's say you have some gate here, here, this one will go here, and then you'll have some output here. So we basically put some numbers here, and then as they go through these gates, they undergo some transformation. So it could be an addition or multiplication, or it could be something more complex than that. It could be like, think about some polynomial, like a formula that you would, multiply it by something raised to power 3 or at constant and things like that.
So maybe like here it's adding some constant, and here it's maybe squaring both of these wires, and so we're just like representing this long complicated computation.
Exactly.
Like and it could really be anything, right? It could be something as complex as an elliptic curve, group operation, or a hash, like anything that we need to do in blockchain world, we can do in this model.
Yep. So this is kind of the way you describe or could visualize R1CS. So now the other scheme that I described is AIR. And the approach there is very different. So here we think about the computation as a circuit. Here we think about a computation as a machine computation, which starts with in some initial states, and that you can think about the state as some set of variables. And then you apply a transition function to the state, so you update those variables in some manner. But you apply the same transition function with every step, and you can execute it for many steps. So if we were to draw it, let's say we have something like this.
So this looks more like what a computer is.
Yes.
Like this is a circuit, and it does one thing. But here, there's just a state transition that's repeated, like a cycle in a CPU that's just repeated over and over.
Yeah. I think a CPU is actually a very good analogy for this, where you have some, state of registers within a CPU, and a CPU executes an instruction, and it updates those registers. And with every instruction, you update some or maybe all of those registers. And you get the same thing here. So you do it many, many times. So you have a very, the same transition function, and then you get to the end. So if we had inputs here as individual wires, here the inputs would be in the initial state, and here the output was like one output here, and then here output would be kind of in the final state.
So each one of these cells is sort of similar to a wire over there. It's just a
yeah. I mean, you can think about a state as where you could put the wires against like these two adjacent rows, for example. But then you would have to have the same wires going for. Yeah, you could actually think of like we would compress this circuit and put them as transitions between these wires, and then we would have to repeat the same circuit over and over between each two consecutive set of steps. So these two different ways. So like in many SNARKs, as I mentioned, this types of arithmetization is being used, and while in STARKs we use specifically this type of arithmetization. And there are a couple of reasons why, for example, we couldn't use R1CS and STARKs, because, well, main reason if we were to use R1CS and STARKs, and I'll explain why in a second, we would not get the scalable, the S would not work there, or at least not that S.
And so I'm curious, are each one of these arithmetizations better suited for different applications?
Yeah, so well, let's go kind of through pros and cons of this, and like I think that will kind of answer the question. So basically, with this type of a computation, what you have to do is you need to fully describe the computation using these gates, which means that if you have a loop, for example, you need to unroll it completely for every number of iterations, that gives you kind of like one thing that it gives you is that flexibility of mix and match. So like once I have this computation described, it's very easy for me to like add another computation that output of which goes as input wires into this computation, and then I have another computation here which takes the output of this one as an input, and so forth. So I can compose them very, very easily together. So that's the big advantage that R1CS is. Here, for example, we have this repeated structure that happens all the time. So if we want to compose them together, so like here I have 4 cells in a row. So if I have another computation that has 5 cells in a row, it's not clear how to put them together. You can't really stack them very easily, one on top of each other, and it basically makes it extremely difficult to compose different gadgets together, so to say. While here you can have like standalone gadgets, you mix and match them, it works out well.
So like if I had an elliptic curve signature verification, I could plug it in with some hash preimage, and it just would work, and I would generate a new description for the circuit, and it's easy.
Exactly. Now, if we talk about like what advantage does this have over this, and why this is scalable and this is not, is that here for the verifier to be able to verify the program, they need to understand the entire circuit. Because the circuit doesn't have repeated structure, you actually need to kind of like read in all the gates, and that means the verifier needs to spend linear time to kind of understand what the program is. There is a way to kind of avoid this, and this way involves pre-processing, and that is also what makes this non-succinct or non-scalable. So you need to have somebody kind of read the circuit, pre-process it, and basically commit to it. and then the verifier can be sure that once they evaluate the commitment or look at the commitment, they know that which circuit this is related to. Now,
sorry to
go ahead.
But that's because like I can tell you everything about this by just saying, okay, it's this one state transition function.
Yeah, you just need to examine one small transition function, and then you kind of can learn everything about this computation.
But with R1CS, it could be like some elliptic curve operation. It could be like a balance check or a range check.
It's very difficult to infer repeated structure from this circuit.
Okay.
Yeah. So, and then one thing to know though, that depending on your application, this pre-processing may not be a problem at all. You might, if you have a very well-defined program, you can do this pre-processing once, and then you're sure, that this is the program. And then if you need to verify against this program many times, you kind of don't lose much in terms of the syncness or ability to do it very quickly. So in many contexts in blockchain, like let's say Zcash verification circuit, when you have a very well-defined program that has been pre-processed once, or you can even pre-process it yourself if you would like, and then you can verify all the transactions using that one circuit. But if you have something kind of like this, then you actually never need to do pre-processing. So it's kind of like a little bit simpler, and also makes it scalable if you have very heterogeneous computations, basically, where there are many different computations where you would need to pre-process potentially circuits as they come in. And then you had a question which I said we'll talk about later.
I think that might have been the scalable succinct question. Which so in practice, like there's not that much of a sort of overhead for most applications.
For most applications, again, they differs. For example, if you wanted to build a virtual machine, I think it would be difficult using R1CS to build a virtual machine. While for air, it's a natural way to describe a computation, or like an easy way to describe arbitrary computations using virtual machines.
So like for Miden, which is the VM that you're building at Polygon, it sort of looks like, you can think about it as like a CPU.
Exactly.
Where every step is verified with a zero-knowledge proof. And so that sort of fits with the air model. Exactly. Yep. I think you can probably do like a virtual machine using recursive proofs, where you have this description of the transition and then you kind of verify it recursively. But this is an alternative and probably a faster approach in many ways to do it. Definitely.
All right. So this kind of covers the arithmetization part, and the second part that I mentioned is the polynomial commitment scheme. So if we can probably erase arithmetization. So polynomial commitments, assuming we have those polynomials, now we need to kind of commit to them so that the verifier can open them at a few points. They don't need to see the entire polynomial, otherwise it will not be succinct. Or scalable for that matter, and you need to be able to open them at a few points and kind of verify this air complies with those polynomials, air or whatever R1CS complies with those polynomials. And there are different ways of doing it. So there are different types of commitment schemes. So two of the more popular ones is KZG, which is frequently used in SNARKs, and then there is FRI, which is frequently used in STARKs. And
so SNARKs, KZG,
yes.
And then STARKs. Oh, you have to write it.
But they don't necessarily have to. You can mix and match, and you can use one. It's just what is more commonly used.
Well, actually, I've heard about this new proving system.
Yes,
it's called
2.
like Plonky 2 or something.
Yes.
And it's a SNARK, but it uses FRI.
Yes, exactly. So, you could also say it's kind of almost like a STARK, except for the pre-processing step, I guess. So it's very close to a STARK. But yeah, so there are different properties of this. So one of the reasons why we use FRI in STARKs is that you don't want to rely on any kind of, you want to be transparent.
So no trusted setup.
No trusted setup.
Like, yeah,
and to use KZG, for example, you do need trusted setup. So that's one of the reasons why if you use KZG with STARKs, that's no longer a STARK technically. So FRI allows you not to use trusted setup. And the reason why, there are technical reasons for that, but for example, FRI relies only on hash functions, and you can kind of do this polynomial commitment using hash functions, and you don't need to rely on any other cryptography.
Whereas KZG
relies on elliptic curve pairings, for example. Oh, I should mention the third one is the IP inner product argument based polynomial commitment scheme. So this one is also used in a lot of SNARKs, I guess, over here. So this KZG, for example, relies on elliptic curve pairings. IPA relies on elliptic curves, or just elliptic curves. And FRI relies on hash functions. So IPA is also transparent, for example. This is an also transparent commitment scheme, so it means you don't need trusted setup. Now, one of the reasons why sometimes KZG is preferred is because the proof sizes are very small. Because you can do because you can use elliptic curve pairings, you can think that you can compress a lot of information into just a few points on these elliptic curves. So like frequently proofs that use KZG commitments are way, way smaller than proofs that rely on FRI or IPA.
And so this is sort of off topic, but an elliptic curve pairing is basically like in elliptic curves, we have the group operation, and so we can think of that as addition. And then a pairing is a bilinear map that lets us sort of impose another operation, and we can use linearity and shrink something. Not to go too off topic.
Yes, no, exactly. And then if we wanted to kind of say that this is probably, FRI has the largest proofs out of the three, so this is large. IPA has smaller proofs, but still in kind of kilobytes.
So maybe tiny,
large. If I spelled tiny correctly. Yes, so this is, so we can get just, if a couple hundred bytes is enough for KZG frequently, a few kilobytes or somewhere in that range is enough for IPA, and FRI, depending on the size of the computation, could be dozens of kilobytes. So that's kind of.
And now what's the speed too? Because we can have
right?
Because we can have fast proofs that are big and small proofs that are.
So interestingly, even though FRI has the largest proofs, they're actually the fastest because computing pairings is fairly expensive. Elliptic curve operations are not as expensive as pairings, but still, require some non-trivial amount of computation. And then FRI relies only on hash functions, which are very, very fast, and they have been made fast over time. And in many cases, you actually have hardware support for doing different, specific hash functions. So it's very, very fast to do FRI proofs.
And so to kind of sum up polynomial commitments, I can take a polynomial, I can commit to it,
yep.
I can hand you the commitment, and then I can prove to you that the value at some other point is correct.
Correct. Well, you need to, you prove that is what you've committed to is a polynomial of specific degree. So you don't. That's I think, and then yes, you open that polynomial at a given point.
Okay.
Yep.
Cool. I think I'm starting to follow along.
Okay, we can probably erase this. So let's go back to the question you asked. So how does actually air arithmetization works, and how do we get those polynomials? Going back to what I drew previously, so we can, if we imagine our computation as a sequence of repeated states of a given, which result from applying transition function to an input, we can think about what we call an execution trace, which is basically a matrix where there are columns and there are rows. So where each row represents a state of that computation in a given at a given kind of cycle, so to say.
So that would be like the variables in the register.
The values of variables at that step of the computation.
So again, not to belabor, but I start with a set of variables here.
Yes.
And then I just do the same state transition function every time, and that could be something like super simple, like I could just add one to each variable, or it could be something really complex, like I could have like a cycle of basically CPU that I can use to verify
Exactly.
EVM transactions.
Yep, exactly. So yeah, so we have this execution trace, and the other important part of this kind of description of there. So the first we've kind of described it as a set of kind of applying transition function, is defining this transition function, or like not necessarily a transition function itself, but defining the relationships between the rows in the table. And the simplest form is that we can take two rows in a table, and we can apply a set of kind of equations to them. And if this equations evaluate to 0, then we say yes, the transition was correct. If any of the equations evaluates non-zero, then we say the equation is not correct. So again, the important aspect of this is that for us to encode the computation correctly, if the transition is incorrect, or if like there was one variable that was not set correctly, at least one of these constraints should evaluate to a non-zero value. So a simple example, let's say, which doesn't actually involve two rows, but well, let me think. Yeah, so let's say we wanted to ensure that values in this column are always, either 0 or 1, and let's call this column like f0, something like that. So what we would do is write this equation f0 squared minus f0, and this should be equal to 0. If we can see that this statement would hold true only if values in this column are either 0 or 1.
Yeah, because 0 times 0 minus 0 is 0, 1 minus 1 is 0.
Right. And if we try to put like, a value 2, it would evaluate to some other value. So this is one constraint that is enforced against one of the columns, but in our overall computation, we want to make sure that we have many of these constraints. I mean, it depends on the system, but it could be dozens, or it could be hundreds of these constraints, or for some larger computations, like an EVM, it could be even potentially thousands. Yeah, so you have a bunch of these constraints, and this is how you get to your polynomials. I mean, there is more stuff here, but basically you can think about it kind of, we need to evaluate these constraints on every two consecutive rows. So like you think, we'll take these two rows and we get some result for this constraint. Then we would take these two rows and we would get another result, and then we would get these two, well, not these two, sorry. These two rows and so forth. And basically we take every consecutive pair of rows and get some result by evaluating these constraints. Now, you may want to say, well, this will always evaluate to 0 on the entire thing. So what's the use of a lot of zeros? So we actually do something else before we evaluate these constraints on this table, and this is called the low degree extension. And to describe, and maybe let's erase this one. What a lower degree extension does is that we take this column, for example, and let's say the length of this column is n, and we would evaluate, we would kind of interpret this column as evaluations of some polynomial on a domain of size n. And not to get too detailed here, but in the domain in this case would be like a multiplicative subgroup in a field that we're working in. So one of the questions is like, how do we know, like, once we know these evaluations, can we like get the polynomial back in coefficient form? And yes, we can by kind of interpolating the polynomial. And because we're in kind of this group, the size of our domain is n, we can, when we interpolate this into a polynomial, we'll get a polynomial of degree n minus 1. And this is kind of like, follows from like high school math, I guess, where if you have, 2 points, 2 points define a line, 3 points define a parabola. So like basically, if you have n points, you have a polynomial of degree of n minus 1. So.
And so are we interpolating with the values in those cells, or just the constraints?
So first step is we're interpolating as just values in those cells. So if you know kind of complexity of different algorithms, you would say, well, interpolation is a very expensive operation. It is, the complexity is of n squared, and this will probably get expensive very quickly. But one of the reasons why we do this in a multiplicative subgroup is because there we can use a much faster algorithms for evaluation, which is specifically like NTT, or number theoretic transform, which is kind of a version of an FTT algorithm. So that allows you to interpolate these polynomials in n log n time, which is makes a world of difference between n log n and n squared. So yeah, so we do this if you erase this ones.
The whole matrix?
No, just, yeah, this is fine. So the next thing would be to, like, let's say we interpolate this and we get another table. And now this would be, let's say we run this, like what is called the reverse NTT algorithm, INTT.
And so I guess we'll just treat that as a black box, and
Yeah.
just say it allows us to interpolate.
Yeah, we will not get into details of how this INTT works, but yeah, what we get here, like this was evaluations of this polynomial. So I would say maybe I should have left more space. And here we'll also get our f0, but this would be coefficients. So we'll get all of these polynomials in coefficient form now, so we'll know, actually the formulas to describe that.
And so we're trying to take this description of a program and we're trying to put it into polynomials, because then we'll be able to do some things. We'll get to this,
Yes,
but
yes.
we'll be able to do some things to prove that our Stark is...
Yes, to prove that all the relationships hold. All right, so the next step would be, so now that we have polynomials in coefficient form, the next step is kind of like, is part of this low degree extension, is to evaluate it over a larger domain. And we do this for purposes of this Reed-Solomon encoding, which I guess we will not get into.
Well, can we talk about that sort of conceptually, like why we would want to, like what it is at a high level and why we would want to do it?
Well, it introduces kind of this redundancy into the structure where that's one, and then I guess once we do this Reed-Solomon encoding, we like increase the size of the domain, and then like it's easier to catch. I guess like when you start querying these different points in this domain, it's easier to catch the dishonest prover if they are trying to like cheat. But I don't know how to explain it better.
maybe we'll get into it with FRI.
Yes, we'll get once we get to FRI, we'll get into it. Okay, so we do this extension, and what this extension does, if you like erase the lower part of this, so I can make the table shorter. Yeah, that's fine, and the same here. And this extension, basically, let's say we want to extend it by 2x or something like that. Basically, keeps the number of columns the same because we still work with the same number of polynomials, but now we have twice the number of rows. So this is 2x extension, and for this we use NTT.
So why do we want twice the number of rows again?
Well, so one of the reasons we want is because we want to like have this Reed-Solomon encoding. I guess the other number of rows, like once we extend this, like this, let's say if I write the constraint here before that, f0 squared minus f0 should be, well, this expression, like if I say our some, c0, this would be our constraint. I should have put an x in there, but fine. Once we evaluate this on a larger domain, not all the values will evaluate to 0. So we'll actually get some specific values for these polynomials. And the degree, if we think about the degrees of these polynomials that we have here, so if we have here degree f0 was...
so C0 would be...
Well, C0 is of degree 2, right? So, but this degree of f0 was n minus 1. So degree of, like once we run each of these rows, like the polynomial that we would get in this column would actually be, degree of, so in this case, the degree of this C of x polynomial, because it is being composed with this polynomial degree of n minus 1, it would be actually like n 2n minus 2, or I guess to make it more explicit, n minus 1 times n minus 1, or plus n minus 1. I think that's the right formula. But basically, you increase the degree of your constraints, and now you have like a polynomial that describes, like, if we didn't do this extension and we try to evaluate this over, let's say, original domain, this C of x polynomial would not fit into this original domain, so we would lose some information in there as well. Yeah, so like one of the things is that here I had a 2x extension, and 2x extension is the minimum what you need to do, but like in some cases, depending on what your constraints are, you need to do a larger extension. So like if I had like a cube here for some reason, so like if that was my thing, then you would see that the degree of this C of x polynomial would be bigger than 2n minus 2. So it would not actually fit into this just 2x number of rows. So you would need to do a degree 4 extension, well, not degree, but the blow-up factor would need to be 4x, because now it would not fit in there. And then if you go even higher in terms of constraint degrees, you would actually need to do much bigger blow-up factor. That's one of the reasons why you may need to do a blow-up factor. There are reasons why you may want to do a blow-up factor, is that the higher the blow-up factor is, given the fixed degree, the fewer queries you need to do. There is more redundancy introduced, like the read-sum encoding introduces more redundancy in the structure, so there is fewer queries that you would need to do later in the FRI protocol, and that makes your proof sizes smaller. So there is frequently a trade-off that you can kind of dynamically tune whether between the proof size and the proving speed. It takes more time to do a higher extension or extension by a bigger blow-up factor, but you need to do fewer queries. So in that case, your proof would be smaller, but it would take more time. Or you can choose to have a smaller blow-up factor, and in that case, your proof would be bigger, but then the computing this would take much less time. And you guys use it very extensively in Plonky too, where like in some cases you do blow-up factor of 256. Yeah. And that makes proofs very small, but they take more time, or yeah.
Yeah, so I think that's an interesting thing with FRI, right? Because if there's that trade-off, whereas in SNARKs, like if you're using KZG, your proving time is a certain amount and your proof size is fixed. But with FRI, we can have really, really fast proofs that are really big, but it's really not an issue because eventually we recursively aggregate them and then we can shrink that final proof. So
yep.
It's really cool.
Yeah. I think, and maybe I should have even mentioned it before, but STARKs in general have more these levers that you can pull at runtime that are not fixed by kind of some given parameters. You can choose different security levers dynamically, for example. You don't have to, like while with SNARKs, once you've chosen your curve and things like that, your security level is fixed. You can't do anything. But here, without changing arithmetization or description of the program, we can make a proof faster if we allow for, or make a proof smaller if we are willing to tolerate lower security level and so forth. So in general, there is much more flexibility and many different levers that you can pull with STARKs than there are with SNARKs.
Yeah, we couldn't generate a circuit with a particular curve and then swap it out because that would ruin our pre-processing.
Exactly. All right, so once we get to the step, I guess let's erase this and I'll draw the table with this constraint evaluations. Yeah, so one other thing that I should have mentioned about constraints is that we frequently want to define on which rows the constraints hold. So like, we can apply the constraints, even let's say this, the original constraint that I draw, which was like f0 of x squared minus f of x. We may not want to hold, make sure, have this constraint hold on all rows. And frequently what we have is this polynomial, we divide this by this vanishing polynomial or constraint divisor, depending on which terminology you use. But for example, if we wanted to, for this constraint to hold on a single point, we could potentially do something like, what is it, x minus, let's say, well, I need to get into generators. So like, let's say, if we wanted to hold on the first row only, we could do like x minus 1. Am I saying something incorrectly?
Is that the, would that be how you, yeah, okay, yeah.
So, and if we wanted to hold this on the next, kind of on a second row, this would be times x minus, you know, in our case, we have this generator of this multiplicative subgroup, which is omega, and it would be omega to the power of 1, so which will be just omega. And the reason it's 1 here is because it's omega to power 0. So, and then we could keep going, like we could say, well, we want this constraint to hold on the next row and so forth, so like x minus omega squared, and that's until the end. So if you think about your like domain that consists of many, many rows, like you would think, well, this multiplication should take a long, long time to do. How is it succinct? Well, fortunately, again, because we're in this structure of multiplicative subgroup, we can very succinctly evaluate this, and I believe the formula is something like x to the n minus, do you remember? I think it's x to the n minus 1. For all of this multiplication.
Just for the vanishing.
Yeah.
Yeah.
X to the n minus 1. So like in this case, all of this like until the very end would basically evaluate to this. So we can replace, if you erase this, yeah, so we can just divide it by x to the n minus 1, and that would give us like a statement that basically says that this constraint should hold on all steps of the execution trace, on all rows. And then if we wanted to say, like frequently for transition constraints, we don't want it to hold on all rows. We want to have the constraints hold on all rows except for the last one. So what we could do is just take this and divide out the last point, which would be, you know, x minus omega to the power of n minus 1. Yeah. So frequently we use this as like, this is the full definition of a constraint which specifies what is the relationship and which rows the relationship should hold on.
So these polynomials encode the values in the rows, and then this is a constraint on those, effectively on those rows.
Exactly.
And
Yep.
And the x has a domain in this multiplicative subgroup that basically like steps through each of the rows.
Yep, exactly. All right, so going back to our drawings of constraint evaluation. So we actually need to evaluate this entire expression for each row. So like when we do our constraint evaluation, I lied a little bit before. We don't just evaluate this, we evaluate this whole thing. And we would get some values here. This is frequently fairly expensive because you need to do divisions and so forth. So there are a lot of optimizations that we do in practice. For example, you know, in our system, what we do is we evaluate only numerators. And then once all the numerators are evaluated, we can combine all the numerators together based on what the kind of the vanishing polynomial is. So for all constraints that have the same numerators, we can combine them together and just divide them once. So, and the way we combine them, by the way, that's another interesting thing, is that instead of like having, you know, as I mentioned, there could be hundreds of these constraints, and we can evaluate them separately and put them in a big table. But it actually frequently makes more sense to kind of like evaluate them and merge them together. So at the end, you kind of end up with a single polynomial. Maybe let's erase this one. And I'll call this polynomial c of x. And this is frequently referred to as a composition polynomial. So we merge all of the polynomials together into one composition polynomial. And this composition polynomial, the way we build this together, or the way we combine this individual polynomials into a composition polynomial, is by using like randomness, random coefficients that kind of, in the interactive version of a protocol, the verifier sends to the prover. In a non-interactive version, you kind of derive from like previously committed to values in a protocol.
So I guess just to step through it for my benefit as a beginner, we have polynomials that encode values in each of these columns, and we can impose constraints on those polynomials such that they satisfy our transition function.
Correct.
Like we had, so like f0 of 1 is this value, f0 of omega I, like we can think of it, it's not 2, but we can think of it as 2.
Yep.
I guess it could be 2, but, and so with that, we can basically force that these constraints are only valid if those polynomial relations hold.
Correct.
And then
exactly.
we can basically compress them all into a single polynomial, but we have to sample some randomness because otherwise it might be possible for a malicious prover to pick values such that they, like certain constraints might cancel out.
Exactly. So, and this is, to be clear, this is an optimization step. Theoretically, once you have these polynomials described and you've computed them all, you don't need to compress them. That still, you could still kind of, let's say, run FRI individually on each of the columns, but that would be fairly wasteful. So we would like to do it, run FRI only once, because FRI actually contributes the biggest part to the kind of the proof size is probably like 80%, if not more sometimes, is actually the FRI proof. So we want to do it only once, and that's why we compress them kind of together into a single polynomial. The other thing to note is that when we do this compression, we need to, as you said, draw randomness. So like depending on which field you're in, you may not get enough randomness. So like if you're in a 64-bit field, this is just not enough for random values. There is too much probability. Well, I mean, not too much, but from cryptographic standpoint, there is too much kind of to live to chance or potentially brute force attacks of some sort. So we need to draw values from a larger field, and that's where, like, for example, we would have to go to extension field. I think that is probably too much to go in detail to go into this, but this is one of the reasons why if you run kind of like in a small field, there is some additional tricks or steps that you need to take to make sure that you have enough soundness in your proof. And
we like small fields because CPUs use small fields, and so it's just more efficient if we can fit one field element.
Right. If we can simplify as you know, multiplications, complexity of multiplications grows super linearly with the size of the.
I've heard it's n squared, actually.
Yes. It was n squared complexity. So going from a 256-bit field, for example, to a 64-bit field is not just a 4x improvement. It's more like 20 or 40x improvement or something like that.
So I guess to hopefully our viewers have stuck with us so far. But we've taken a program and we converted it into this matrix where we start out with our initial values.
Yep.
And we define our state transition function. And then, so we basically convert this program, the execution of this program, into a matrix where every row corresponds to like the state of the program at each step.
Correct.
And then we take that matrix where all these values throughout the entire computation, and we convert them into polynomials. And with those polynomials, we can basically enforce that, like for every row, that those constraints that we care about are satisfied.
Yes.
And then we have some more tricks to kind of compress those polynomials into something that's a little more easy to work with.
Now that we have this polynomial, as we discussed, we need to prove that it's of specific degree. And this is where polynomial commitment scheme comes in, where you need to commit to this polynomial. And we could use KZG, as we said before, but in star context, because we want to have this T, we use FRI. And we also want to be very fast. That's why we also use FRI. All right, so what does FRI do? FRI basically takes this polynomial and very efficiently allows us to verify that, well, takes a commitment to something and very efficiently allows us to verify that this commitment to this set of values is actually a polynomial bounded by some degree. Now, again, the naive way to do it would be to send the whole polynomial or a whole set of evaluations and let the verifier kind of read that and verify that it's actually the correct kind of polynomial and so forth. But that would lose the succinctness or scalability and probably would not work in our context. So what FRI does, it's a very efficient and very ingenious algorithm. It basically breaks the polynomial. So if we now think about, if you erase this one, yeah, we can do the whole thing. So we'll now draw our polynomial horizontally. So let's say this is the commitment to the polynomial. So what we do
So, sorry to stop you, but what does this look like? What are the values in these cells?
Well, so the values in the cells would be also elements in the finite field. So this is you can think about as an array of elements in the finite field. And then FRI has this step where we reduce the size of this polynomial by half with every step, or it could be by more than half. But basically, we repeatedly apply this.
So are these coefficients, or what do those elements correspond to?
Well, in FRI, this is actually evaluations of the polynomial. These are not coefficients. I believe in KZG there are coefficients, but in FRI it's actually evaluations of a polynomial over the domain. So this would be, if we had our domain of size n, and we did the 2x extension, this would be the domain of size 2n. So, we would have evaluations of a polynomial, but it may help to think about it like initially as coefficients, because we'll see. So like if you think of this as a polynomial of degree actually n minus 1 contained in this here, you can reduce it and you can reduce the degree of that polynomial. So like the process actually called the degree respecting projection. So we'll degree respecting projection, and what it does is that with every step folds the polynomial onto itself almost by half, and reduces the domain by half as well. So we basically go from n over 2n to then n to then n over 2, and then until at the very end we can have just a single value. And at that point the verifier can send that single value to the prover can send that single value to the verifier, and the verifier can, as long as we can convince that this degree respecting projection was done correctly at every step, and we get that final value, we can convince the verifier that our set of values is actually a polynomial.
So we send this, and then, so if I'm the prover, I do this process, and then I send you this, and then I'm going to go through we're going to play another game so I can convince you that this actually commits to the right polynomial. Right.
Well, so we need to be convinced that that commits to the right polynomial, but also we need to be convinced that these degree respecting projections have been done correctly. And the way we do this is, so let's talk about first what a degree respecting projection would be. So the way to think about this, if we have a polynomial, which is like, let's say a simple one, x to the power 3, some, I guess, a b to x to the power 2 plus c x to the power, or just x, plus d, right? So this is our polynomial. The way to fold it in half could be just take the odd and even coefficients of this. So we could group this as, ax cube plus cx plus b, might be is like a 6 squared plus d. So like we think about this as two kind of separate parts, and then we can just move x out of here, and what we would get is x here, a x plus c, and here we would get bx squared plus d. And this is a b. So inside here we get two polynomials of the basically same degree now. So like this is, and you can notice, well, I guess it's not half, but if you think about the domain size, it's half. You need half the domain size to do this. So the way we combine them together is we again take this random coefficients and like add them up, and we kind of like end up with a single polynomial now with degree like a, b, c, d, e. So let's say it would be e x squared minus some f. So this is our new polynomial after we went through this degree respecting projection, where like the coefficients e and f are basically kind of a combination of coefficients from these two polynomials mixed in with some randomness, so that the prover cannot pick like the values that will make them cancel out. And then we repeat this process again and again until we get to a smaller value. Now this, and I probably should have started with that the FRI actually consists of two things. There is a commit phase and a query phase of the protocol. So the commit phase is kind of doing these things where prover does this degree respecting projection and commits to each successive layer and sends the commitment to the verifier. And then once the commit phase is done, we then start the query phase where the verifier now asks the prover to send, picks random points in this domain and asks the prover to send all the relevant values for each layer from this domain. And then the verifier queries, gets those points and makes sure, computes, it's slightly different expression, but it's an expression that allows verifier to be convinced that these formulas were computed correctly at each step.
Mm-hmm. So we can't, again, just send all of this information because it wouldn't be succinct. So we have to send some small subset of it to get the scalability property that we want.
Yes, exactly. But by the end of this query phase, the verifier now knows that this is a polynomial of a given degree. And then there is some more work left here to how do you tie this polynomial back to the original trace. And there are several methods to do that. One of them is the deep method, where you actually do another sampling outside of the domain, and that allows you to kind of tie all the polynomials together. We didn't cover it in this session. But the other approach is to kind of query the original execution trace in multiple points in the consecutive rows and do this constraint evaluation and have enough of those points that tie back to this polynomial as well. So there are kind of different ways of doing that. I think the deep method has an advantage because you reduce the number of these computations that the verifier needs to do to figure out on how many, what are the constraints at a given point. But yeah, so this is the FRI protocol.
Cool. So now we have our arithmetization. So we've taken we've defined our program, and we execute the program outside of a zero-knowledge proof. And so that execution allows us to fill out that matrix with all of the values from each step of the computation.
Correct.
And then we take that matrix and we can convert that into polynomials for each column. And we can enforce constraints on those polynomials that basically make it possible to check that state transition is valid. And so now we have those polynomials, which we compress, but I can't, as the prover, just send you that polynomial because it wouldn't be succinct. Its size would be basically linear in the size of the computation. So then we run FRI to get a succinct commitment to the polynomial, which is in the form of queries in this. So I guess not to take a tangent, but we make this a Merkle tree that allows us to.
One of the things that I didn't mention is that it's more abstract commitment, but in reality, as for commitment purposes, we just build Merkle trees and send the roots of this Merkle tree to the verifier.
Bobbin, one thing that we missed, what does FRI stand for? So
FRI stands for Fast Read Solomon IOP, which itself stands for Interactive Oracle Proof of Proximity.
IOPP.
IOPP, yes.
Yeah. Cool. And so an interactive Oracle proof in the ZKP context basically just allows us to sample a few points in such a way that we can guarantee with high probability that some polynomial relation holds.
Correct.
Cool. Well, this has been a great conversation. I've learned a lot, and it's been a pleasure.
Same here. Thank you.
Thanks.